Now for something completely different. All right, yeah, so I am Chris Grundeman, and like many of you, I spend most of my time helping companies build network infrastructure. But first of all, actually, I'd like to thank you all for being here. We're like right after lunch on Wednesday, the third day of NANOG, so I just really appreciate everyone showing up and being here and being awake. That's pretty awesome. Quick show of hands, who went to the Exploratorium last night? Awesome, yeah, that was fun. And I had a lot of fun there playing with a bunch of the models that were kind of demonstrating how different aspects of the physical world work. And that's interesting because what I'm going to talk about is a model for understanding how networks work, I think. And this is probably nothing super new in here in this talk, but hopefully combined in an interesting way that might help the way you think about building networks now and into the future. So we are a little behind schedule, and I do have about 68 slides, so buckle up. We're going to be here for a while. We're going to jump in, though. So network model. So first, I think we should probably set the stage by understanding what do I even mean by a network model, right? So I think we know what a network is. We need to pass packets. We have to forward frames. There's routers and switches, all of your favorite middle boxing that kind of populate in between the switches and routers, and then obviously the connections that tie them together. So hopefully at NANOG, we're pretty solid on what a network is. But what's a model, right? I'm not talking about an HO scale train set. Obviously, we probably don't want to 3D print a physical representation of your network. That's probably not super useful. So what I really want to talk about is a conceptual model, right? But what does that mean? Wikipedia says that a conceptual model is a set of concepts, not a very handy definition. An abstraction of real things. I think that's a little bit more interesting. We're starting to get to what we want to talk about. A representation of a system. That's getting a little warmer. Really what we want to talk about is something that we are using to help people know, understand, or simulate a subject, right? So just a way of thinking about something is really what a model is, in this context anyway. So before we jump into what I'd like to introduce as the new model, as I would call it, we need to first kind of look at the old model. Obviously, there's a number of different network architectures out there, but I think the most commonly used, and especially in like enterprise and campuses and data centers, is this 3-tier hierarchical network model, right? So you've got your core, big switches, passing packets, the aggregation layer where your kind of services live, and the access layer down below to kind of get those ports out. What's interesting is, the data center network model looks suspiciously similar, but we've changed one word to distribution instead of aggregation, which is kind of curious. Obviously, I wasn't there when they made that naming choice, so I don't really know why that choice was made, but I have a suspicion that it has something to do with this client-server model where what we're really doing is aggregating, client connections, sending them across the network, and then distributing them out to the servers. Obviously, there's a return path there as well. And this was where, not only is there that 3-tier model of core, distribution, and access, but there's this other 3, which is LAN, WAN, and data center. And I think one of the reasons we tend to split these networks apart, there's a couple of reasons, right? Physical boundaries and things like that. But one of the reasons is just complexity, right? And so you're limiting your failure domain, but also just kind of your cognitive domain of what you have to understand in any given piece of the network, and you can kind of build them differently and things like that. And really, this is probably sideways, because actually what we're talking about is this actually looks like a kind of a north-south client-server model, which is starting to hint towards what we're talking about, but I don't want to get too far ahead of myself here. So again, those 3 tiers, right? That core layer, which is usually big iron, just passing packets, really fast forwarding is kind of the point there. Aggregation and distribution, this is where I would say network services live here, right? They live on these boxes. That's where you're dealing with policy or kind of firewall rules, load balancing, doing routing, that kind of stuff is all at that layer. And then the access obviously is just about connectivity into that. Okay, so that's the old model. Obviously, I can't talk about kind of the old 3-tier model without mentioning leaf spine or the folded clause network that we're talking about more today. So what I think happened is virtualization, right? Also like object-oriented programming and microservices and things. Basically, we changed traffic patterns in data centers from purely north-south to mostly east-west. Also, we're turning up and turning down services really quickly, so things have to adjust much faster. There's mobile workloads, right? You can kind of move virtual machines around, that kind of stuff, and massive scale. Now, all these things aren't necessarily tied to each other, but they all did happen about the same time, and I think those are the main forces that kind of spurred this idea of the leaf spine network coming into favor. Clause is not an acronym. There's a guy named Charles Clause back in 1952 figured out a way to hook together crossbar switches to cost effectively implement an almost infinite scaled network. So that's what kind of allowed telephony to flourish. Pretty cool. There's some cool little algorithms you can use to figure out what the actual capacity is and the number of links and stuff. And what we're doing now today is folding that up so we kind of get this leaf spine network model. Spoiler alert, that's not the two tiers that I want to talk about today. Okay. So before I talk about the new model, right, I want to look at why we even want to talk about a new model. There are some problems with this kind of three-tiered model and some reasons why it might be a legacy model. I think there's kind of three reasons that the three-tiered model is showing its age, right? So one is directionality. We talked about this a little already, this idea of the difference between north-south traffic versus east-west traffic, right? So that directional change makes things different and makes you want to be able to move traffic across the data center more than just getting it in or out, right? And I think that's also happening, in other places as well. And then, if we can call it directional, the difference in scale, right? Where do you want to scale up by just buying bigger and bigger boxes, or scale out by adding more small boxes or even virtual devices, right? So the second problem is in resiliency, right? Spanning tree sucks. Blocking half your links just doesn't make any sense. And then, this plays back into that scale up versus scale out. But if you want redundancy in a three-tier model, you're building in redundancy at all three layers in order to provide redundancy for the whole system, which also probably sucks because you're paying for a lot of boxes, again, that aren't even being used because of spanning tree blocking half your bandwidth. And really what all this comes down to is this idea of hardware centricity, right? So you're talking about this kind of vertically integrated mainframe type device that we call a switch or a router. And especially when you look at like that distribution and aggregation layer where those services live, and those services are tied to those boxes. So if you want to add a new feature, you've got to replace hardware. That's not super great for network reliability and uptime, right? If you're trying to get to whatever number of nines you're shooting for, having to actually shut something down to turn it off to replace it is really, really hard on those uptime numbers, right? Also, because that physical connectivity is part of this, and you're talking about physical devices, where you actually connect things matters. So you actually have to worry about where things live and how they're connected in and how the packet forwarding goes through that. This is one of the reasons why things like microsegmentation didn't take off very early, because routing everything up through a big firewall and back down isn't super practical, right? So being able to do other things makes that more practical. And then also, in a lot of cases, this is this kind of manual box by box configuration. And then, like I said, feature velocity, right? So am I willing to upgrade the software package on my router that's potentially going to take down my whole network for one feature or not? And that question leads to probably a little bit slower agility in being able to add new features and add new services to your network, right? Okay, so network virtualization, right? This is kind of the thing that is allowing us to get past this, right? I would say virtualization and automation together are probably the keys to kind of move into this new model, right? So network virtualization, the first piece is network function virtualization, right? Creating virtual network functions. So taking things that hardware devices used to do and moving those into software. So you can do this with almost all kinds of things. There's some really interesting stuff where we've been able to use CPUs to pass packets better. I built an ISP in the early noughties where there was no way we were going to get to 10 gig scale on the Linux bridging routers we were using. You can do that now, right? You can pass a massive amount of traffic through servers now, which is really, really cool, both on Microsoft and Linux. It's allowing a lot of stuff to happen. One thing I would note for anybody who's creating virtual network functions, simply taking what a device does and putting it into a virtual machine and virtualizing that, and that's kind of cool. But what you really want to do is rethink the way that those functions work, and maybe actually what your device is doing is composable into a set of different microservices that can be set up, and then you can really get kind of granular in how you do updates and changing things. So there's a note for anybody who's creating virtual network functions. Think about how you can leverage the way you're virtualizing them to do totally different things than what you would do by just kind of taking a physical box and making it a virtual machine. Beyond that, then the next thing is, beside individual devices, there's a network we can virtualize, right? So this is kind of the standard way you draw a virtualized network. Makes total sense. I think actually there's a little bit simpler way to draw it is if you look at this network, maybe the smiley faces are users, the check marks are our applications, there's some X's in there which are routers or switches, and what we're really doing when we're talking about network virtualization is we're saying, I don't really care about that physical network. What I want to do is make the connectivity look like this, right? And in most cases, we do that with overlays. The hottest ones now are like VXLAN and Geneve are talked about a lot. A lot of people, I think, freak out about overlays, and just the whole concept of tunneling traffic and that kind of stuff. I think that it's really important to remember that they're not new, right? We've been using VLANs, MPLS, GRE, IPsec, like I mean, all this tunneling technology. We've been overlaying networks for a long, long time. Also, even just like the whole OSI model is a way to understand overlaying networks, right? Your optical ring of fiber in a city has very little to do with the way the Ethernet connectivity across that metro Ethernet network might work versus the way you're actually IP routing between your own services or applications, right? So like the overlays are just the way we do networking. So don't be too scared. So, all right, finally, the new model, right? There's two ideas I think that really kind of, or what like led me to this way of like thinking about this networks in a new way, I think, kind of, right? So the first one is what I'm calling switch inception, and the second one is router explosion. So we'll look at each one here. So the first thing is this idea of switches and switches, right? And the comparison of a folded cloth network, like the leaf-spine network, versus what a multi-chip switch looks like. And the potential to maybe have more visibility and control by exploding that switch, right? So let's take a look at this leaf-spine network, right? The folded claws. You have spine switches that are all connected to, every spine is connected to every leaf's connected to every spine, pretty standard. But let's, if we pull the sheet metal back on a multi-chip switch, like a big chassis switch, what does it look like? Well, it's got fabric chips that are connected to every NPU, and every NPU is connected to every fabric chip. So that's interesting. So just in case you missed it, I'm going to go again. There's the claws network, multi-chip switch, very, very similar, right? So it's interesting, you can think about an ECMP network as just a switch, right? In some ways. And the second thing is this idea of router explosion, right? So if you're using some kind of SDN controller, or even just like an automation framework where you've got something driving that you can look at that controller as a routing engine, or routing processor, supervisor, or whatever. And then you virtualize these network functions. Those virtualized network functions become like PFEs, packet forwarding engines, or line cards, right? And then your tunnels become virtual circuits between this. So you can almost look at this as one big router, right? So to illustrate that, we can look at this is essentially what a router looks like. You've got routing protocols that are feeding information into the routing engine, which maintains a routing table. It's then feeding information out through routing protocols to other devices. It's also talking to the PFEs or line cards, which are holding their forwarding table, right? The fib is down there, and they're using that to connect to physical interfaces to kind of make the whole thing work, right? It's essentially how this all works. And what's interesting is if you look at, like an SDN or a controller-based network, it's super similar. Again, you've got routing protocols and APIs that are feeding into a controller, which maintains the routing table. And then it can also feed out information through protocols or APIs. It's talking to virtual network functions that can live almost anywhere, right? They can be on your servers. Potentially, they could be on the supercomputer you carry in your pocket, potentially anywhere. And they maintain the forwarding table, which then talk to physical or virtual interfaces, right? So again, router, SDN, very similar, right? So, maybe you can start to see where I'm going with this. If we take this kind of network, the way this looks, and we say, okay, instead of kind of dealing with all of these like physical boxes in the middle there, if we kind of look at this as pushing those as virtual network functions into the edge devices, and you've got a kind of distributed, centralized control plane there in the middle, those exclamation points are kind of your SDN controllers, or whatever automation engine you have driving this thing. You can look at this as one big distributed router, essentially. Now, obviously, you still need physical connectivity, and that's where we get this two-tier idea, right? So looking at the underlay as a core switch, and the overlay as an access router, right? There's some characteristics that I think are interesting or important to remember here. The underlay is essentially what you want as a non-blocking ECMP. One thing that I'll touch on a little bit later as well, but the internet is a pretty cool ECMP network to use as an underlay in general. Also, you want this to be resilient and high bandwidth, and then it's going to be made of physical devices, right? For now, no matter how much we love software, ASICs and cables and things like that just have to be there to make a network work. I don't think that's going to change anytime soon. So again, you can make this rock solid, IP fabric that is your underlay, and then on the top you build tunnels that can do hashing to take advantage of the ECMP. You can do policy-based routing, source-based routing. Once you've moved the intelligence of the routing into servers instead of resource-constrained routers and switches, you can do almost anything you want, right? Some really, really cool stuff. with application-based routing and some interesting things there, right? And then obviously these are virtual devices. So again, right, what we're really talking about is connectivity and hardware, that rock-solid platform to build this on, and then routing, policy, services, security, all that stuff in software above it that can kind of live wherever it needs to. Okay, so why is that interesting, right? So when it hit me, I thought I could think about this thing as core switch is actually your whole underlay physical platform, and the access router is actually your whole kind of virtualized software services overlay. But why is that interesting, right? And I think there's a couple reasons. One is, just theoretically thinking about this, it allows you to focus on what matters. So if you kind of look at this in the two-tiered way, you can look at, okay, what does the physical underlay need to provide for my network, which is, the rock-solid reliability, high bandwidth, all those things. And you can really focus on just doing those things. And then, okay, when I'm building services, what do those need to provide? And you can just focus on those things. So kind of that separation of church and state, being able to focus on what matters, I think is interesting. Just from kind of a conceptual way of looking at the network, you can really kind of stop trying to do everything in the device and look at where that actually should live. In practicality, I think one of the biggest things is scale, right? So if you move a lot of the intelligence of what your network needs to do into servers, you essentially have, maybe infinite is too big of a word, but you can throw servers at this thing all day. So you can do almost anything you want. Also, like the update cycle, right? So because you've detached, if you think about, if you build a rock-solid underlay that you don't change very often, it's just passing high volumes of packets very, very well, and you don't touch that, then you can innovate in services, right? So you can change things at the service layer, and they only impact people who are using those services. You can do, smaller surgical updates, things like that, adding features, all of that, without affecting the whole system, which I think is why this is super interesting. And essentially what you're doing is kind of creating this universal network platform, right? So by having, the central kind of, whether it's, SDN or just an automation framework or whatever you want to use there, you're pushing out consistent policy to all of your devices, kind of looking at that as this one single access router. That's super interesting. Also the same thing, because you're kind of looking at this in these two planes, it provides simplicity so you can think about these things, model these things in your own mind, and then potentially more visibility as well, because you're tying this all together into a single system versus looking at box by box devices. And then also, like I said, because it's universal network platform, I think there's some interesting things around, being able to potentially unify domains. This idea that the WAN is the new LAN. If all of my employees, right, if you're looking at corporate networks, right, my employees are walking around with phones in their pockets and laptops, and then everything they're using is either in, a public cloud or a SaaS-based service. So, where is my network, and then how do I manage my network? And I think this model can help you lead down that path of how to figure that out. Right, so I try not to create new buzzwords too often. I think cloud integrated network is better than SDN for this kind of idea, where we're kind of embedding the cloud into the network, right, which is pushing compute resources further out. All this talk about IoT and the need for compute further out, the edge cloud, right. Also taking the network to the public cloud, which is this idea of multi-cloud and how do I actually connect all these things together. And that's where once you realize you need those two things, right, if you're pushing these things out, then I kind of need this universal network platform, which is, I think, what this model helps to understand. Obviously, disaggregation and virtualization, automation orchestration, telemetry and analytics are all pieces and parts of kind of using this model more practically. Use cases, right? So I think if you look at some service providers that have been built recently, they are already doing this, right? So I'm sure some of you maybe have already fallen asleep and just like, yeah, I get it, man. This is how we do things. That's fine. Obviously, like I said earlier, kind of using the internet as an underlay. That's the whole idea of SD-WAN, which is kind of pretty interesting. And then on the enterprise side, I think is super interesting as this kind of moves into large enterprises and then down. As they're using more public resources, the deparameterization of the corporate network is really interesting to me, and how we actually deal with that. One of the sponsors actually has a cool solution to that. If you want to know about it, you can talk to me. But just this idea of like, how do we actually connect people to the things they need to connect to when a lot of the networks and services, or a lot of the networks and hardware that those things live on don't actually belong to me, right? My user owns his own phone. Some big cloud provider owns the servers. Some internet service provider owns the connectivity between them. So what do I actually do? And this overlay idea, I think, is a way to potentially regain control and manage that. If I don't want a controller, so you do EVPN, right? And so this is kind of digging into specifically into the data center use case, which I think this model is more broad than that. But you can do this without true SDN, right? You can use EVPN, and then if you just use automation to do configurations, you can still get some of the benefits of this. You really do need that automation framework, I think, whether it's through sold as SDN controller or something else, to really get the benefits. Another thing, I can't talk about this without somebody saying, well, what about OpenFlow? What you really need to do is do native SDN. Overlays suck. As I've mentioned the word a couple times, there's this thing called the internet. It's already out there. We're not going to convert every device on the internet into OpenFlow-based devices. And even if we did, you probably wouldn't give me access to your devices to me to send OpenFlow commands to them. So that's not really going to work, right? You don't want to have to replace everything to make this work. So overlays are pretty cool to just not have to worry about that. Another interesting thing that I've thought about in this is this idea of the return to end-to-end, right? So a lot of us place bets on IPv6 of like trying to get, back to the end-to-end model and getting rid of all these, NAT devices and all these middle boxes. Well, the cool thing is if you're moving all services to software and you're pushing that to the edge, you potentially have a clear network path between the devices, and you can put those services and things at the actual, back at the edge. Kind of, I don't know, we'll see. So, in conclusion here, right? One thing I do want to remember is, the map is not the terrain. Obviously, this is a model. It's just something that I think is kind of helpful as a way to think about networks. It's not, going to be exactly, it's obviously not a reference architecture or anything like that. It's just a tool you can use. And in final summary here, right? So overlays are normal. I think models are helpful. It is a digital world. Software is king. Like I think that needs to feed our thinking, even the network space. Use the two, right? Think of your underlay as a core switch, your overlay as an access router, and I think you'll be able to see the problems you're facing in potentially a slightly new light. Any questions or comments thinly disguised as questions?
I'm Spencer Dawkins, one of the transport area directors at the IETF. You said the thing about overlays are normal, and what I was getting from your presentation is that they're more than normal, that you want to make them kind of a first-class part of the internet, because it seems like to me that where we've gotten so far has been pretty ad hoc. With it's like, well, we can encapsulate this and we can tunnel that, and so it seems like you're trying to make this a more well-structured idea than we've gotten to it, so far, which I really like. I was curious about whether it makes a difference if somebody is using their overlay network to provide another cloud enabled network. And I am curious about whether you're advocating that the underlays fix a lot of the challenges that we have today, which we talked about during, as recently as in this room yesterday during the P4 tutorial about fragments and and extension headers and things like that, which are a challenge, but maybe you're making the set of challenges small enough to where they'd be more tractable.
Hopefully,
in the underlay network. And I'm curious about what you think the managing overlays and underlays look like if you're moving into a world where there's a lot of encrypted traffic.
Yeah, those are all good questions. I don't know that I have great answers. Specifically, I think the encrypted traffic thing is definitely interesting. But again, I think if you're, one of the reasons that pushing services as close to the edge as possible is interesting is that perhaps you can do kind of whatever, middle box type magic you would have done in the middle. Now you're doing it at the edge, at the place of encryption, which is, potentially helpful. Now, whether or not that order of operations actually works, depending on who you trust to see the traffic before you encrypt it is maybe another question, but I think it's possibly helpful.
I'm stepping down after 3 terms as transport area director, and I think what you just said there is one of the most helpful things that I've heard on this very challenging process. Thank you.
Thank you. All right, thank you.